Assalamu alaikum warahmatullahi wabarakatuh. This is Dr. Ali El-Moursy in Digital Logic Design DLD, lecture number 28, part 2. We continue with the counters. In the last part, in the first part of this lecture, we actually discussed the 4 characteristics of the counter. If you have answer to those questions, so the design of the counter will be just piece of cake. Now let's go and implement or design a full counter, okay, from A to Z. So the example that we want to take in part 2 of this lecture, okay, design a 3-bit up self-triggered counter. This is the heading of the question, design a 3-bit up self-triggered counter. The first thing when we read the problem of the counter, okay, using T flip-flop, okay, this is our first time to design using T flip-flop. We designed before the 2's complementer using D flip-flop and using JK. And in this example, we will design using T flip-flop. Okay, so the first thing that we need to do here is actually to answer those 4 questions. Question number 1, direction of counting. Okay, it is explicitly mentioned in the problem here that this is an up counter. Question number 2, range of counting. This is binary counter, 3 bits. 3-bit binary counter means counting in the range of counting for binary for 3 bits. So the range of counting is from 0 till 7. I have 8 counts. Okay, this is the second, and this is actually the rule of thumb. The rule of thumb. The second question about the counter is actually very important, as we will see. Okay, now I will mention the rule of thumb later on. Let me just continue in the answering the question. Question number 3, sequence of counting. There is no mentioning here about any hopping, that it's not jumping. This counter is not jumping from one state, it go directly sequentially. So it counts 0, then 1, then 2, and until it reaches 2, the count 7, and automatically will go back to 0. Okay, nothing is mentioned about hopping here, so that means it is sequential counting. It is a sequential. Okay, now last question, triggering. This is self-triggered. Now we need to learn how can I, from answering those questions, successfully build the state diagram for the problem. Okay, state diagram, as we know, state diagram means circles and arrows. The circles represent the number of states. And the rule of thumb that we want to mention here is that answering the second question, a range of countings equals to a number of states in the state diagram. So if this counter, binary counter, 3 bits, that means it has total 8 counts. 8 counts mean 8 states. Like, what if I'm having a 2-bit counter, binary counter, 2-bit binary counter, have 4 counts, that means I have 4 states. If a number of states equals the number of counts. Rule of thumb for the counters. Okay? If the counter range actually counts 6 counts, whatever those 6 counts is, whatever they are, okay, that means the counter has 6 states. So automatically, from answering question number 2, I can actually identify or start building the state diagram. My state diagram here has 8 circles. 1, 2, 3, 4, 5, 6, 7, 8. So I have S0, S1, S2, S3, S4, S5, S6, and S7. 8 counts, 8 states. Now, I dislike how those are drawn, so I'm just drawing them in a nicer way. 1, 2, 3, 4, 5, 6. 6, 7, 8. S4, S5, S6, S7. Okay? How many? The second very important hint here is the last one. اللي هو مين؟ الtriggering. Is this self-triggered or external triggered? This is self-triggered counter. That means it does not have external triggering. That means through the clock, the counter will count from one count to the next, to the next, to the next. Means the circuit does not have any external input. The golden rule for the state transitions is that a number of state transitions from each state, the arrows are going out from each state equals to the power a number of external inputs. How many external inputs do you have here? 0. There is no external inputs. 2 to the power 0 is 1. That means I have only one arrow going from each state to the next. Now I will use the answer. يبقى the answer of the second question give me the number of states. Okay, 8 states. The answering of the last question give me the number of arrows. Now, through the answer of the first question and the third question, the direction of counting is counting up. So if I have this count for count number 0, S0 is count for number 0, that means the next state is count number 1. Okay? So direction of counting, I'm counting up. And the sequence of counting, I'm going sequentially. So from count 0, I go to count 1. From count 1, I go to 2. From 2, I go to 3. 3, I go to 4. 4, I go to 5. 5, I go to 6. 6, go to 7. And 7, go back to 0. If this is the state diagram for the counter. That's it. Okay? I successfully built a state diagram for a 3-bit up self-triggered counter. What's left for me is to start from the state diagram into the other steps of the design. The second step of the design here is actually do the state assignments. How many states? Number of states are 8. Since I have 8 states, so I can recognize the second golden rule for the state diagram is the number of fifes. Number of states equals 2 to the power a number of fifes. So the number of fifes in this case, since I have 8 states, that means the number of flip-flops, number of fifes equals to 3. And this is, by the way, inherited in the problem. It's from the beginning, it tells me it's a 3-bit counter. 3-bit counter, so 3 flip-flops. each counter or each bit is one output from the FIFI. Okay, so what's left for me is to do the state assignment. Now, since I have 3 flip-flops, that means I need a table to actually indicate which state will be assigned to which combination of my state inputs. Here I have actually 3 bits, and usually we call those flip-flops flip-flop A, flip-flop B, and flip-flop C. And here is the state. We have actually how many states? We have 8 states. Split into 2 halves, 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 into 2 halves. So I have for total 8 states. S0, S1, S2, S3, S4, S5, S6, S7. Okay? So I have to do what's called the state assignment. State assignment, we go sequentially. So 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1. 0, 0, 0, 0, 1, 1, 1, 1. Accordingly, this state S0 is corresponding to A, B, C equals to 0, 0, 0. Here, 1, 0, 0. Here, 0, 1, 0. Here, 1, 1, 0. Here, 0, 0, 1. 1, 0, 1. 0, 1, 1. 1, 1, 1. And that's it. So I finished the state assignment. Now I'm ready for the solution. Since we have a limited space, so I wanted to erase all of the information here in order to go to the second component in my design, which is the state table. So we finished building the first parameter of my design, which is the state diagram. And also I did the state assignment. So right now, I want to give myself a space, so I will erase all of the explanation here. Okay, done with this. I wanted to complete my design. In order to complete my design, my next step is the state table. I need to build the state table for my circuit. Now the state diagram will help me to successfully build my state table. Can I build a state table? So let's take this area for our state table. State table has the state. It has 3 partitions here. If you still remember, okay? I have here the input, I have here the output, I have here the states. Now, for the inputs, how many state inputs? Okay, if I'm doing an input output analysis, input output analysis here is very simple. How many state inputs? State inputs are 3, A, B, and C. I have 3 flip-flops. Do I have any external input? None. يبقى external in none. طيب. State outputs. State outputs, yes. A of t plus 1, B B of t plus 1, C of t plus 1. Do I have any external output? The answer is no. So this is actually my input-output analysis. Accordingly, I have here how many columns? I should have 3 columns for the inputs. Actually, I have here only the, what we call the, this is actually the part for the present state. There is no external inputs, and I have only next state. There is no external there is no external outputs. Okay, so here I have their names as follows. Okay, here I have 3 of them at the input. لهم مين؟ A, B, and C. For the output side, I have also 3 of them. لهم مين؟ A of t plus 1, B of t plus 1, C of t plus 1. So I have 3 columns for the inputs, 3 columns for the outputs. That means how many rows? I have total 8 rows. I have total 8 rows. Total of 8 rows. I have here for the input side, I just fill it 0, 1, 0, 1, 0, 1, 0, 1. For B, 0, 0, 1, 1, 0, 0, 1, 1. For A, 0, 0, 0, 0, 1, 1, 1, 1. And as the state assignment indicates, this is actually S0, this is S1, S2, S3, S4, S5, S6, and finally S7. How this circuit is transitioning from one state to the other, okay, according to the state diagram, okay. So in the state diagram, if I am in S0, I will go directly to S1. When the clock comes, when the triggering is happening, the trigger here is the clock. So from S1, I will go to, from S0, I will go to S1. يبقى 1, 0, 0. If I'm in S1, I will go to S2 اللي هي 0, 1, 0. If I'm in 2, I will go to 3 اللي هي 1, 1, 0. If I am in 3, I will go to 4, 0, 0, 1. If I am in 4, I will go to 5, 1, 0, 1. If I am in 5, I will go to 6, 0, 1, 1. If I am in 6, I will go to 7, 1, 1, 1. Finally, if I am in 7, I will go back to 0, 0, back again. Yep, this is direct mapping from the state diagram to the state table. Right now, we are, by the way, we are ready for the design. Yep, we drive the state diagram. From the state diagram, we got the, we got the we got component number 2 اللي هي state table. Now, before I go to the state equations, I can start in building component 4 اللي هي circuit diagram. Can I start the circuit diagram? Yes. Why? Circuit diagram is 2 components. Sequential side and combinational side. كده ولا ايه؟ We agree on this? We agree on this before. And I have here a combinational side. The sequential side is already designed. Why? Because I know the number of flip-flops and I know the type of flip-flops. How many flip-flops do I need for this circuit? I need 3 FIFIs. So I will draw the first flip-flop, the second flip-flop, the third flip-flop. Those flip-flops have names. They have names. We give them names. So we call this flip-flop A, this is B, and this is C. What type of FIFIs we used here? We decided to use the T flip-flop. So I have here TA and output A and A bar, TB, B and B bar, TC, C and C bar. Okay, so we drive the equations. We build the sequential part. Sequential part is done. Okay, what actually left for me is the combinational circuit. What are the inputs of the combinational? It's A, B, and C. The output of the combinational are TA, TB, TC. We decide to use the T flip-flop. So that means I need here the intermediate in out. I need columns for my intermediate in outs اللي هم مين؟ The 3 outputs of the combinational, which are the 3 inputs of the sequential, TA, TB, and TC. I want to drive them. Remember that the equations for them are not simple. From the characteristic equation, A of t plus 1 equals to TA XORed with A. B of t plus 1 equals to TB XORed with B. C of t plus 1 equals to TC XORed with C. So I cannot build a direct relationship between what I have, which is A of t plus 1, B of t plus 1, C of t plus 1, and the inputs. Actually, I wanted to drive those. If I have TA, TB, TC, that means I can design this. So that means I need here to use the help of what we call the excitation table for the T flip-flop. Okay, so the excitation table is driven from here. I want to draw 2 tables. The first table is the characteristic table of the T. Do you still remember it? This is the characteristic table. The characteristic table tells me that if I have here T, I have here Q of T plus 1. So the characteristic table tells me 0. Sorry. The characteristic table is simply have only one input. So I have only 2 options. So I have T and I have Q of T plus 1. Okay? So characteristic table for the T flip-flop is 0, 1. If you still remember it, if T equals to 0, I have Q. If T equals to 1, I have Q bar. We already did that when we developed the T flip-flop. Now, I want from the characteristic table to build another table. It's called what? The excitation table. excitation table is actually showing something completely different. This is the excitation table. You don't have to drive it. We will drive it once here. But if a problem to be solved by the T flip-flop in the exam, I will give this table for you. So don't worry. Q and the Q of T plus 1. And here I have T. Here I have T. Right now, we need to drive the excitation table. Here I have 4 options. Q and the Q of T plus 1 either equals 0, 1, 0, 1, 0, 0, 1, 1. How can I get 0, 0, Q and the Q of T plus 1? What value of T shall I put? Definitely I should put T equals to 0 because they are similar. Here also they are similar, so T should be 0. Up here they are different, so I have to put mean T equals to 1 in both 2 cases. So this is the excitation table for the T flip-flop. We will use this to fill in the table here. Okay, now let's go into the details of our circuit. So for TA, can I drive the TA? I have column for A and I have column for A of T plus 1. 0, 0, so I go here. 0, 0, I have to put 0. 1, 1, I have to put 0. 0, 1 or 1, 0, I have to put 1. So accordingly, I can drive TA from A and A of T plus 1. 0, 0, TA should be 0. 0, 0, 0. 0, 0, 0. 0, 1 means I have to put 1. 1, 1, 0. 1, 1, 0. 1, 1, 0. 1, 0, 1. So I drive the first column for TA. Similarly, I can do for TB. B and B of T plus 1. 0, 0 means 0. 0, 1 means 1. 1, 1 means 0. 1, 0 means 1. 0, 0 means 0. 0, 1, 1. 1, 1, 0. 1, 0, 1. So I drive the column for TB. Third, for TC, I have C and C of T plus 1. 0, 1 means 0, 1 means 1. 1, 0, 1. 0, 1, 1. 1, 0, 1. 0, 1, 1. 1, 1, 1. All the TC should be 1. That's why T flip-flop is the preferred flip-flop to build counters. Why? Because the combinational circuit is very simple. Is it really simple? Yes, it is. Why? Go and check. What should be the value of TC? TC all ones. Do you really need a K-map? Do you really need a K-map? Okay. So now let's have some space here. So I will remove the definition of the problem. I'm still in the design of the binary counter, 3-bit binary up self-triggered counter. So now I want to complete the design. Okay, I'm giving myself a little bit of space here. So do you really think we need a K-map for TC? Even if I did, okay, TC, الكي-map شكلها عامل ازاي? Here is the K-map, okay? But remember that this K-map contain all ones. So I expect that this K-map will be all ones. 1, 1, 1, 1, 1, 1, 1, 1. Where is the contour? The contour is gathering everything together. And X, X bar, A bar kicked out, B kicked out, C kicked out. We discussed this before. This is the unity function. So TC simply equals to 1. That's it. Agree? Now I will go to TB. Can you get TB? TB is 01010101. Can you see it? So TB is also very simple to design. TC, all what I have to do, TB, all what I have to do is connected to the input C. So I can take the input C from here and connect it in the feedback here to mean to TB. You don't believe me? Let's design for TB. TB, K-map. A bar A, B bar B, C bar C bar. 01010101. 01010101. Where is the contour? Here is the contour. Prime implicant on prime implicant. A bar cancel, B bar cancel. I have only C, and this is essential, so it is simply C. So T C is connected to 1. TC connected to 1. TB connected to C. Agree? Lastly is TA. Another K map. Here I'm using the K maps. Okay? K map. Okay? The last K map is for the last one, which is TA. A bar A, B bar B, C bar C bar. Okay? TA is 0001, 0001. Can we do it? Yes. 0001, 0001. Prime implicant. Here is the contour. This contour has the name A bar. A is cancelled. It is B, C, and it is essential. Okay, I have no other contours. So simply يبقى هنا يبقى TC equal to 1, TB equals to C, and TA equals to BC. Can I implement that? Yes, for sure. But this is the first equation for the intermediate input. This is the second, and here is the third. يبقى TA needs an AND gate. I need an AND gate, and this AND gate is simply connecting the B. It's connecting B to C. So coming from the feedback B and C to be connected to give me TA. So the circuit from the combinational side is so simple. Here is 1, here is C, here is BC, okay? And this is the implementation for the 3-bit binary counter, okay, using T flip-flop. That's why we always prefer to build the counters using the T flip-flop. Am I done here? The answer is no. The answer is no. Why no? Because you have to show me the equations. Okay, I know. So these equations are after driving the TA and TB and TC. I have to substitute here. So the final equations لهي component number 3. Okay, the final equations can be written here. Okay, so I have here component number 3, which is the state equations. State equation tell me that A of t plus 1 equals to TA. What's TA? TA is BC XORed with the input A. B of t plus 1 is TB. Where is TB? It is C XORed with B. C of t plus 1 equals to TC, which is 1 XORed with C. The 3 equations here representing the state equations. So from the state diagram, we got the state table. From state table, using the excitation table or the assistant of the excitation table, I get the equations for the TATBTC. Using K-maps, I get the equations, so I can design the combinational circuit. We design the sequential circuit. Connecting them together, I get the full design for the circuit diagram, and I can also drive the state equations. From the state table, I get the state equations, I get the circuit. So my answer is complete. Agree? Make sense? Now the homework. Your homework. The homework is homework. Design BCD counter. I want you to fully design a BCD counter, okay? Definitely, when I say BCD, it default, it is up counting, self-triggered. Up counting, self-triggered, okay? And BCD means the range from 0 till 9, and go back, from 9, go back to A to 0. So design the BCD counter, okay, up counting using T flip-flop, okay? This is your homework for the counter exam. Now, I can play a lot of games here for the counters, okay? Changing any of the 4 requirements will give you a different type of counter, okay? One example that we will discuss about the counters, we will discuss it, inshallah, in the last lecture of the semester, lecture number 30, okay? We are now finishing lecture number 28, part 2, and this is the first application for the synchronous sequential circuits, the counter circuits. The next lecture, lecture number 29, will be about the registers, okay, which is the second very important application for synchronous sequential circuits. Thank you, and see you in lecture number 29.